Thank you, everybody. Very excited to be here. I'm going to be talking about the Unison programming language and this really interesting technique of compilation via partial evaluation, which we're using in the Scala-based Unison runtime. And this is work I've been doing with Arya Irani, who's one of the Unison open source contributors. He's sadly not here, but he's been helping a lot with the implementation. So the talk is it's two parts. So first part, I'm going to kind of motivate and introduce the Unison programming language. And then kind of part two, I'm going to be talking about this technique, compilation via partial evaluation, which we're using in the Unison runtime that's being implemented in Scala. So let me kind of start. We'll start by just motivating the Unison language. So Unison, it's this language for building distributed systems. And I think the way that we currently build distributed systems today, it kind of has some problems. But it sort of starts out okay. You start out your programming in Scala, and you're in this little box of building your Scala-based microservice, and things are great. You have all this nice composability and abstraction and the ability to reuse code and all these nice things. But Scala and really just our programming languages in general, they can't really talk directly about an entire distributed system. So they really are only talking about what like a single node is doing. And the way that they talk about kind of the rest of the system is by, like sending blobs of JSON, say, out into the ether. And there's kind of some code there of like doing parsing and serialization of the JSON code. And then maybe on the other end, you have some other Scala-based service that you've written, and it has some JSON parsing and serialization that it's doing. And then, okay, you have these services, but you realize you want them to be elastic. You want to scale up and down the number of instances. So you're doing things like, you need to set up an auto-scaling group in AWS and connect that to an elastic load balancer, and pretty soon you have a whole bunch of these microservices, and they're all talking to each other, and you're stringing together all these different technologies to build a complete system, and you build this crazy Rube Goldberg machine, and like it kind of sort of works, but you feel sad. Or at least I feel sad. And so, so I feel like there's a few things that I don't like about this way that we have of building systems today. And so kind of the first obvious problem is it's actually a ton of work. It's a lot of code that you need to write. It's a lot of things that you need to glue together. But then the nature of the work is also kind of different than sort of ordinary programming, in that it involves what I would say is a lot of unguessable and arbitrary knowledge. So there's kind of a difference between, when you learn about a cool new data structure and you're like, wow, this data structure is so amazing, and look at all the neat things you can do with it. Or, I learned about this new way of factoring code to achieve, more composability, more reuse that I didn't know about before, and that's really exciting. And when you learn about these things, it's like, you feel like you're understanding things that are kind of more deep, more fundamental, that are sort of logically derived from first principles, and maybe those principles are applied in surprising ways, but you feel like all the knowledge is kind of just connected back to some fundamental things, and that's just really exciting. That's what's, I think, great about computer science, about programming. But then when you're building a distributed system, you have all these things like, configure your elastic load balancer to point to your auto-scaling group. And it's like, how do you do that? It's like, I don't know. It's just some arbitrary procedure that you just have to know. And when you build a larger system, you have a ton of these different things that you all need to know about. And And that's, you know, I wish things were better than that. So what could we maybe have instead? So I think the vision, the thing that I'm excited about is what if you could program any pool of distributed compute resources, any pool of nodes, as if it were a single computer. So all that kind of nice composability and reuse and abstraction, all those nice things that you have when you're working in your little box in Scala, what if you could get that same feeling and those same benefits when you're programming at a much bigger scale? So, and that's kind of the idea behind Unison, is that no matter how big a system you're building, whether it's running on one node or 100,000 nodes, or whether it's even an elastic computation that's growing and shrinking the number of nodes it's running on, you should be able to describe the entirety of that system with a single program. And so that may not make a whole lot of sense, and so I'm actually going to show a little bit of Unison code, and you'll maybe get a feel for what it's going to be like programming in Unison. So just a little bit of background on the language. So Unison is a functional programming language. It's open source. It's MIT licensed. It's been kind of a long R&D project. I was experimenting with a lot of different things. I was working on like a fancy editor for the language at one point, but sort of more recently, just been focused on building out Unison support for building distributed systems. And it's kind of, the project is kind of exiting its kind of R&D phase and really just focused on getting a release out, hopefully soon. And yes, it does have this Scala-based runtime, and I'm going to be kind of talking about the sort of this really interesting technique that we're using in the runtime. Okay, so let me kind of introduce a little bit. I just want to kind of give a taste of what programming in Unison is like. So, okay, just a little bit of syntax here. So in Scala, here's the syntax for applying a function. In Unison, you just put the arguments separated by spaces. So it kind of follows Haskell in terms of the basic syntax. In Scala, here's function definition, and then here's that same function written in Unison. And you can see we actually left off the type annotation, so we could do that if we want. It would be inferred, or you could give the annotation, and it would be checked that factorial has that type. Okay, so the interesting thing is that, okay, so you have this kind of basic functional language that you can use, but then the interesting thing is you can define computations that move between nodes. And so this function here it's going to compute factorial, but it's going to compute factorial on a different node. And so it takes in a node, which we're calling Alice. So you can think of a node as it's kind of this opaque thing that it represents the location where computation can occur. And so we take this node in, which we're calling Alice, and then we say, at the Alice node, go ahead and compute factorial. And when Unison runs this program, it's actually going to move the computation, control the computation to Alice and compute factorial. And then you can see that the return type it's now no longer just returning a number, it's returning a remote number, which is indicating that there's this computation might be happening on multiple nodes. And okay, so and here's an example of a multi-node computation in Unison. So now we have a do block so it's kind of like a for comprehension in Scala, and we're going to compute factorial 3 on the Alice node, compute factorial 7 on the Bob node, and combine them. We're assuming that in this example that we just sort of somehow know about the nodes Alice and Bob. But the interesting thing is that this also works even if we're obtaining a reference to a node kind of dynamically in our program. So in this is kind of the same structure as the previous example, but now we're taking a provisioning action, which is of type remote node. So this is something that it's defined elsewhere in our Unison program, but it's going to be something that is going to give us back a node. at runtime. And so we provision the Alice node, we provision the Bob node, and then we compute factorial at Alice and factorial at Bob. And so what the Unison runtime will actually be doing when it runs this program is potentially it will be dynamically deploying the definition of factorial and any of its dependencies that are needed to those nodes that we just provisioned. So so that's kind of, it's a very important but and unique thing that the Unison runtime is doing, is that it's actually doing this runtime code deployment. And so yeah, I think that's kind of the basic idea. And then just using that primitive of the at function, and there's a few other primitives. You can actually build up very very interesting functions and systems with not too much code. So I wrote this little distributed Mapreduce function, and I'm not going to go through it in detail, but we're actually forking off little computations to do all the mapping, and then we're also building this like balanced tree of reductions and doing the reduction in parallel. And then here's an example of actually using it. And again, we're actually so this implementation of distributed word count is it's not working with necessarily a static cluster of nodes. It's actually taking a provisioning action that is going to of type remote node, and it's actually going to be essentially like spinning up a little cluster of nodes just sort of temporarily for the duration of this Mapreduce computation. So it's very easy to define these elastic distributed computations that are kind of growing and shrinking in size. And you don't just have to have like a static pool of nodes that you're working with. So cool. Okay, so hopefully that gives you an idea of what this what programming in Unison could be like, and hopefully that sounds great to people. But we're kind of asking a lot of the Unison runtime. So if Unison is really giving you this ability to move an arbitrary computation from one node to another, then that kind of implies that the Unison runtime needs to be doing this dynamic deployment and compilation of code. So there's this question of like, okay, well, how do we need some way of representing Unison code and shipping it around and possibly recompiling it. And there's this question of how do we do that? We could use maybe some low-level representation, LLVM, JVM bytecode. I mean, I guess we could write our own, just-in-time compiler from scratch, but that's going to be a ton of work. And we don't want to take a decade to be able to use Unison and have it be reasonably efficient. So kind of the simplest thing that could possibly work would be to just send the Unison abstract syntax tree between nodes and then just interpret the abstract syntax tree. But that's going to be slow, right? So somewhat surprisingly, it does not have to be slow. And so now we're kind of in part two of the talk. I want to show this. I mean, to me, it's this almost amazing idea that for about the level of effort of building an interpreter, you can get something whose performance approaches native speed. And it's using this technique of compilation via partial evaluation, which I'm going to tell you all about. So the big idea, and don't worry if this doesn't quite make sense yet, but the big idea is that when you partially evaluate or specialize an interpreter for a program, that is compilation of that program, or it can be thought of as compilation of that program. So this is not a new idea. There's something called the Fudamura projections. It goes back to the 80s, and I remember reading this blog post about it. It was a while ago, and it was amazing. It's sort of a mind-blowing thing to kind of read about, but I didn't quite know what to do about it, or what to do with it. But sort of the thing that is maybe not as well known is that you can exploit this principle to build you can sort of do that partial evaluation yourself, and just kind of using ordinary Scala code that is written in a sort of a funny way, you can build this interpreter that can be partially evaluated, and you kind of get like a just-in-time compiler for free, just using sort of regular Scala code. And it sounds sort of magical and like, how is this possible? But I'm going to show you, and it's really cool. So first, what I'm going to do is I'm going to show a very simple programming language that's just an abstract syntax tree in Scala. We're going to write an interpreter for it, and then see why it's slow, and then we're going to use this technique of compilation via partial evaluation to get something that runs a lot faster. But at first I want to kind of talk a little bit more about why are interpreters for programming languages slow. So there's a couple reasons. So the first reason is that interpreters are doing instruction decoding and dispatch. So they're looking at the syntax tree or the bytecode representation, and they're inspecting each instruction or subtree and saying, oh, what kind of thing is this? Oh, it's an add instruction. And then once it knows what kind of instruction is, it goes and does some useful work. But there's some overhead to actually inspecting the tree. And we'll see an example of that in a minute. So the kind of next thing that makes interpreters slow is that it's kind of due to the first reason, but as a result, you have this very unpredictable sequence of machine code that ultimately ends up getting executed. So you no longer just have a relatively predictable sequence of instructions. It's now like you have this very branchy code that you essentially have like a branch after each instruction, and it's not really known what instruction is going to be after each branch. And so so in a modern CPU, modern CPUs do a lot better when they have a whole bunch of instructions all lined up and pipelined, and they're just kind of burning through your CPU kind of one after the other. And there doesn't need to be any delays waiting for instructions to be fetched from the cache or from even main memory, things like that. So that's kind of another source of overhead with an interpreter. And then kind of the final thing is that, when you have this, you don't really have a nice big block of static code that you would typically have a whole bunch of optimizations applied to. You have this very branchy code, and you can do optimizations before you pass it to the interpreter, but you don't sort of get all the same advantages of like statically or even dynamically compiled Java or Scala code, where it's like you end up with a big block of code and the JIT can do a bunch of optimizations. So 3 sources of overhead here. And so the thing I'm going to show is that really all 3 of these sources of overhead can be eliminated via partial evaluation, just by writing your interpreter in kind of this funny way in Scala. So, all right, so let's go through an example of how this works. So I have an expression type here, just an AST, which we can think of as it denotes a function from a vector of doubles to a vector of doubles. And there's just 6 instructions. So I'm just going to go through each of them just to make sure we understand what each of them does. So num 0, 42, it's going to set change register 0 equal to 40. It's going to set it equal to 42. Okay. Plus 0, 1, 2, it's going to set register 0 equal to register 1 plus register 2. Okay. Decrement 3 is going to take register 3 and subtract 1 from it. And then copy 1, 2 is going to set register 1 equal to register 2. And then kind of the more interesting instruction here is loop, which is going to take the body of the loop, which is decrement register 1, and it's going to repeatedly execute that the body of the loop until, in this case, register 1 is 0. So register 1 starts out as 12, and we're just going to repeatedly decrement it until it reaches 0. And so maybe a more realistic example of using loop would be you'd have a whole block of instructions that are getting executed as the body of the loop. So not just one decrement. Okay, so that's our programming language, and very simple, but it's not completely useless. So the true test of whether a programming language is useful or not is can you compute the nth Fibonacci number? And yeah, you can actually do that in this little language. I'm not going to go through this code in detail, but I kind of transliterated it to, or showed kind of what the equivalent Scala is on the right here. And so yeah, you can do some useful things with this language, even though it is kind of a toy. So let's go ahead and write our interpreter for this language. So we're going to take in an expression, and so rather than taking in a vector of doubles and returning a vector of doubles, we're going to try to do things a little more efficiently and just take in an array of doubles, and we're going to mutate it. And okay, so anything that we're doing to this array of doubles is kind of useful work. But anything that we're doing to inspect the expression, like when we're pattern matching on it or anything like that, that's kind of overhead of the interpreter. So we kind of start out in our interpreter, we're going to match on our expression, and okay, the first thing we do is we hit the first case, is it a num? And so there's a certain amount of overhead of checking, okay, is this subtree a number? And okay, once we figured that out, then we go ahead and do some useful work of we set the destination register equal to n. Cool. Let's keep going. So next case, we have plus, and again, there's some overhead of checking, oh, is it a plus instruction? But then once we figured that out, we go ahead and do some useful work of setting the destination register equal to the sum of two other registers. Okay, so then the other cases are going to be similar. Let's get down to loop, because that's kind of one of the most interesting. And loop, it's going to be, again, some pattern matching, overhead, checking, is it a loop? And then, okay, I called into this little subroutine, which let's see what's going on there. And so far, so good in loop. We are, we have this while loop where we're checking to see if the register is 0 yet. But then the body of the loop, ooh, this is no good. So we're actually, in the body of the loop, we're calling interpret on the body of the loop. So each time through the loop, we're paying that same overhead of interpreting and doing all that pattern matching. So, and then it could actually be even worse than this. So we might have a slightly different expression language where the halt condition was not a static register, but it was actually an expression that returned a result. And then in that case, we might have interpreter overhead in also checking the condition of the loop, as well as having the overhead in the body of the loop. Anyway, so you kind of, there's a lot of red stuff, a lot of overhead happening here. And, so first of all, yes, we have that overhead because of instruction decoding and dispatch, all that stuff in red. It is resulting in this very unpredictable sequence of machine code. So it's, you're getting like CPU pipeline stalls, things like that happening. And then we're not getting the usual suite of JVM optimizations applied to the assembly code that ultimately gets generated. And so you kind of put all these things together, and it's pretty easy to have an interpreter that is between 10 and 50x slower than native code. And just as a kind of a frame of reference, like Python is which has like a C interpreter of Python bytecode, is I think it's around 50x slower for sort of straight line, just pure Python performance. And so these interpreters could actually have quite a bit of overhead, even in interpreted languages that have been around for a while. So one kind of thought is like, okay, well, if the problem is just that there's it's like the ratio of the amount of overhead, pattern matching overhead, to useful work that the interpreter is doing. So one kind of thought is like, okay, well, maybe we can just introduce these kind of composite instructions that do more stuff in between, cycles of the interpreter. And so you might say like, oh, okay, we have plus and we have copy, so let's go ahead and introduce plus then copy. But the thing is, you might actually have to go pretty far down this road to get good performance or performance approaching native speed. And also it's just a tremendous pain as a compiler author to generate this crazy instruction set. So it's nice to have a very simple set of core primitives of the language, and just be able to get good performance by combining those. So, but maybe if a more kind of principled approach along these lines would be something like a tracing JIT, which would actually be discovering at runtime essentially these composite instructions. And that's kind of one way of thinking of what a tracing JIT is doing. But I'm not going to talk about tracing JITs. So instead, what we're going to do is partial evaluation. And we're just going to do this in Scala without no fancy frameworks or anything like that. We're just going to write our interpreter in a slightly different way. So our original interpreter looked like this. It was, just took in the expression and this array of doubles, and it returned unit. So our new version of the interpreter is going to take in the expression, and it's going to return a function from an array of doubles to unit. So I'm going to call this the compiled form. So this function from array of double to unit, that's the compiled form. But we're not going to just implement it in the same way. We're actually going to do a bunch of work before we return that compiled form. So and I'm going to call this partial eval because that's what we're doing. We're partially evaluating the function, given just one of its arguments. And so let's go ahead and start writing partial eval here. So we're going to be returning this compiled form. And the first thing we do is we pattern match as before. We check to see if it's a number, but it's after we check to see that it's a number, then we return this compiled form, which is just something that modifies the array. So that work of inspecting the syntax tree to determine that's a number, that's happening kind of in the first stage, really before we've returned the compiled form. Okay, so let's look at plus. Again, we're doing the pattern matching. We figure out that it's a plus, and then we return this compiled form, which is just a function that mutates an array. And I guess the key thing is, if you look at those those functions that mutate an array, it's like you could have written those functions yourself, just in Scala. Like, they have no memory of the fact that they were generated by inspecting a syntax tree. They're just kind of like regular Scala lambdas, and you could have written them yourself. And yeah, they have no memory of the fact that they were generated using by doing this inspection of a syntax tree. So that's kind of a key thing. And then so loop is sort of the kind of maybe the most interesting case is, yes, we're going to compile the body of the loop, but we're only doing that once. We compile the body of the loop, we get back something which is this compiled form, and then in the body of the loop we are executing that compiled form multiple times. So we're compiling once and then running it multiple times, versus what we were doing before is we were actually interpreting the body of the loop multiple times every time we went through the loop. Okay, and then last case is block. We go ahead and compile the first instruction in the block. We compile the rest of the block, and then we return a compiled form that just runs those two compiled forms in sequence. So I guess the key thing here is that at the end of the day, we get back a function that just mutates an array. And the fact that we produce this function by inspecting a syntax tree is kind of forgotten. And we just get back this function that it mutates an array. and it's going to run as fast as any other function that just mutates an array. So let's kind of go back and look at those sources of overhead that we had back when we wrote this as just a regular interpreter. Okay, so we had instruction decoding and dispatch. Well, we specialized all that instruction decoding and dispatch away because we're doing that kind of in the first stage before we return the compiled form. So all that overhead is gone. The fact that we had an unpredictable sequence of machine code, that is actually going to go away because the JVM does some very standard but important optimizations of doing devirtualization and inlining. So that loop body here, which we're evaluating multiple times, the JVM, when it eventually just-in-time compiles this overall loop, it can see that function that you're calling in the body of the loop, it is always the same function. This is not like a megamorphic call site or anything. It's just always going to be calling the same function. The JVM can devirtualize and inline that function, and you can end up with the same block of code that gets compiled as if you sort of manually inlined this. So the JVM helps a lot with that. And then the final thing is that after this inlining happens, you end up with a big block of code that the JVM can be applying its whole suite of optimizations to, just like if you were sort of statically compiling some Java or Scala code. And so you kind of put all these things together, and you can end up with performance with it, which is within a factor of 2 of just straightforward Scala code or Java code. And so here's I actually went ahead and did this, and I have it's like a table ratio of the runtime. So we're summing up a million numbers. So Scala was the fastest. I did a couple different versions of the partially evaluated interpreter. And one of the representations I chose, it was within a factor of 2. And then you can see the interpreter was about 10 times slower than Scala. And so, this is pretty cool. It's like, okay, we first of all, we didn't need to write our own, garbage collector or just-in-time compiler. We didn't need to spend, a decade doing all that stuff. We got access to the JVM, so we can call, Java any sort of JVM functions we want. We have a ton of flexibility in how we do that. Just like when you're writing an interpreter, you're not constrained to like Java semantics or anything like that. You can kind of have your interpreter work however you want, and it's actually really fast. And it's just kind of, I just feel like it's actually amazing. That it actually works, and that it could be this simple. So. First of all, I don't know, is anybody else like feeling that's like, can this really be true? Like, I don't know, that was kind of my reaction when I, sort of learned about this and saw that it could work this well. So the Unison runtime is, it is using this approach. So the one caveat that I will give is that it's very sensitive to what choice of representation, what representation you choose for your compiled form. So in the example that we went through, the compiled form was a function that mutated an array of doubles. But maybe that representation's not so good because you have like array offsets being computed, you have maybe array bounds checks happening, and things that maybe contribute some overhead. So maybe you want a slightly different representation where it's not taking an array, it's taking in like some sort of machine type with just some mutable fields, and maybe that's more efficient. So you do have to like think about, what you want that compiled representation to be, and sort of maybe optimize it and tweak it to get good performance. But still, it's amazing that you can get such good results with without any sort of fancy frameworks or having to write your own JIT or generate x86 assembly or anything like that. And then it's also very flexible, so the Unison runtime, it can support proper tail calls, even though the JVM doesn't kind of support that natively. And then the other really interesting thing, which we haven't tested yet, but it seems like very possible, that if you simply compile the same Scala code via Scala.js, the JavaScript runtimes do the same kinds of optimizations, and jitting that the JVM does. And so I actually think that the performance when compiled via Scala.js I think it would actually probably be pretty similar, or you could end up with something that's very efficient to run also in JavaScript. So potentially Unison would be this great language for building distributed systems kind of on the back end, but then you could also use it on the front end as well, and that would be pretty cool. So I want to mention a couple just connections related work. So I mentioned the Futamura projections. There's also a project by Oracle. It's called Truffle and Grail. It's kind of a bigger framework for doing compilation via partial evaluation, and I think that you could probably get even better performance using something like Truffle and Grail, but it's a bigger bigger kind of framework, and I think it's pretty neat that you can get such good results just writing kind of ordinary Scala code, no fancy frameworks or anything like that. And then I kind of mentioned tracing as another approach to getting rid of interpreter overhead. There's a very interesting project called RPython, which it sort of will generate a tracing JIT for you if you write an interpreter in this kind of subset of Python. So that's another interesting project. And then so I would say if you're interested in this, you can follow along on the blog unisonweb.org and also on Twitter. And then just wanted to give a shout out to Arya Irani, who I've been working with on the runtime stuff. It's been a lot of fun working with him. And then also just thanks to other contributors and advisors who've been helping with Unison over the years. And that's all I have. So if we have some time for questions, then happy to take questions. Yes.
So the partial evaluation seems to remove the dispatch on the leaf nodes, but parts of your AST, like the loop and the block that go down, you have another call. So you'll still have some dispatch. You correct in the evaluation?
Nope, that's not correct. So if we go back to, let's go back to where we do that. Oh, I'm sorry. So the question was, okay, the partial evaluation, it removes overhead for the leaf nodes, but what about, so the leaf nodes like the add and like num, but what about the things like loop where you have, that are not leaf nodes, don't you still have interpreter overhead for those? This is actually it's very critical to understand this. So if you look at how loop is defined, we do call partial eval for the body of the loop. Yeah, but we do that before we return the compiled form. You got it? Yeah. Cool. All right. Yeah. So, but that is really, it's a good question, and it is crucial to understand. And that's almost like the trick is, like, the leaf nodes are sort of more obvious, but the fact that you can even for the non-leaf nodes, you can still go ahead and compile the body of the loop once and then execute it multiple times. That's maybe wouldn't be as obvious. Any other questions or?
Yeah, I have a question.
Yes.
So you use this as a solution to a microservices-oriented system.
Uh-huh.
But to me, this is a solution to a niche problem like Spark solving, where you have one system or application that is too large for one single node and not necessarily a heterogeneous environment where you have all different kinds of
Okay, I'll try to repeat the question. So I guess the question is this kind of like Spark? Or I guess maybe how would this work in a more heterogeneous environment where you have, not everything is written in Unison, something like that? So yeah, I think what I would say is that with Unison, you could build an entire distributed system in Unison, and obviously there'd be a lot of advantages to doing that because Unison is great for that. But then you could also use Unison just to build even a single microservice, and it could fit into a larger system that is more heterogeneous. And yeah, there would even be advantages to using Unison just for a single microservice, because even for a single microservice, you do have things like responding to failures and doing auto scaling and all sorts of things like that. So yeah, I definitely want it to be a language that you could adopt very gradually, maybe just starting with one microservice. And of course, the more of your system that is written in Unison, the more advantages that you can make use of. But yeah, I don't want it to be like the type of thing where it's like you have to literally throw out all your existing code and just rewrite everything in Unison, because that's kind of not really going to work. So yeah, you could kind of start very gradually. At least that's the idea. Yeah.
How is Unison configured to actually run on something like AWS?
I don't know. Maybe come talk to me after. Yeah. Cool. Okay. Yeah. Maybe one more question.
Just about this partial evaluation. When it exactly called, from the perspective of the distributed system? Is it calling on each node when you send the ASD to the node, then the partial evaluation will convert it to the code, or
Right.
it is during the deployment, runtime, caching sort of things? Or?
Yeah. So it would be. It'd be sort of at the point where you need to transfer a computation to another node. You'd be taking the Unison abstract syntax tree, you'd be sending it to the target node, and then that target node would be doing that partial evaluation. And it may actually it may have some parts of that computation cached, so it will already essentially have them compiled. And the target node can make use of that, but even if it's not cached, I mean, it's still, pretty fast. It's not like, I mean, you already have to serialize the syntax tree and send that, so you're already sort of paying this like linear cost of serializing all that computation, and so also doing the partial evaluation, it's like another kind of linear cost of you have to crawl the syntax tree once.
So the profiling was included both interpreting and running. I'm thinking that when you're interpreting, no matter what is the method of interpreting. So in profiling, are you just profiling the compiled unit or the interpretation plus running that compiled unit?
Okay. So the question was about, you mean like profiling for it to be compiled?
Yeah, I'm thinking how much time does it take to, because you're sending the SD to the node and it should be interpreted, and we have the compile unit. The compile unit is very fast, but the interpretation, getting that compile unit would take some time, right? So if it's not cached or if we don't have anything there, wouldn't it be faster than?
Yeah, so I mean, I guess the question is, okay, I'll try to summarize. What happens? So when you first do that partial evaluation, you end up with a Scala function, say, and that Scala function is just going to be potentially interpreted at first by the JVM before it gets just-in-time compiled, and so there might be some initial slowness of. Yeah, so, yep, I mean, I think that is potentially, just like any kind of other JVM program, your entire program is not JITted up front, and it gets sort of incrementally compiled. But yeah, I mean, I think you can still get very good performance out of this. And I mean, I think it's just sort of amazing that it's, so little work on the part of the compile author. So cool. All right, thanks everybody. Yeah, definitely. Feel free to come talk to me after and ask questions, and I'd love to hear what people think, and yeah, come chat.